All right, boys and girls, a little live recording here, back at the drive-thru with some of my faves ever, Alex, Colin, and then all my multi people. I got to meet Carson this year. He's been great. Who we missing from? Oh, and Luca's not here, but also one of my lifelong faves. Differentials. We just watched the video. Okay, the differential. Obviously, this is so important that it is the fourth calculus class. Do you know that? After you get done with Calc 1, Calc 2, Calc 3, the final calculus class is called, anybody know? Differential equations. Okay? And essentially, think about differential equations as a way to create slope fields, vector fields, force fields, by using parallel curves that are in a family. Okay, we'll get to that more. We're not there yet. All right, so I got to save some time somehow. I know that this involves a differential but to me, I have no idea why this shows up into this section. This is exactly how you've been finding the equation of a tangent line all along. When you see f of x, what does that usually make you think of? Y. So this is y minus y1 equals, and when you see the derivative at a point, what does that usually make you think of? The slope times x minus x1. Okay? So not taking too much time to focus on this, but we will do a quick example. Find the tangent line approximation. So the function's f of x equals 1 plus sine of x. So what's the derivative? What's the derivative of that? Cosine of x, right? Positive. And then we want it at the point 0, 1. So our x value equals 0. Our y value is 1. Okay? And so this is going to be y minus 0 equals f prime, y minus 1. Y is 1. Excuse me on that. Y minus 1 equals f prime of 0. Cosine 0? Is that 1? Cosine starts up, right?
Yep.
Yeah. So equals 1 times x minus 0. So you get y equals 1x plus 1. Okay, yeah, boom, there it is. Now, some mathematicians think this is important. Between negative 45 degrees, this part of the sine and cosine curves is approaching very approximately to 1, which means, I guess, for every radian or piece of a radian we would go over, we go a piece of radian up. I don't think that's important, but I have heard of other mathematicians that say it is. Okay, so that's it for the tangent line estimate. Again, I don't know how that involves differential equations, but it is a good way to approximate. Okay, now, I'll probably get in trouble, but luckily no one watches these videos because it's not as simple as like multiplying, but it's also not that far off. What's another way of writing f prime of x? What's another notation for that? Yeah, and then if f of x represents y, we can actually write that as dy dx. Okay. So then the differential is the derivative times dx. I know that like you may not know where we're going with that, but if they ask you to find a differential, you just take the derivative and multiply it by the dx. So now it's time to think about, well, what is dy and dx? What are they? Anyone want to throw out? It's like a really small change in y and a really small change in x. Now, which variable is usually the independent variable, the one we can do whatever we want with?
X.
X. X, we choose X and Y has popped out. That's okay. Most people don't get that quick because we just like skip past that part in algebra. So what they're saying is we can use this to see how much output will change if the input changes by just a little. So like that might be if I worked at McDonald's and I wanted to control the cost of burgers. We go back to this a lot. We talked about this last year. What are all the factors that goes into the cost of a cheeseburger at McDonald's? Let's start throwing them out.
Cost of ingredients.
Okay, so beef cost, bread cost, onions cost, labor cost, thank you,
Power cost.
gas cost, and electric cost, power cost, all these things. Well, that's a lot more than just one variable, just so you know, because at the end of this is multivariable. That means we could figure out if y represented the price of a cheeseburger, how much would the cost or the price of a cheeseburger go up if x was like the price of gas? Then we could break this down and look at how different changes in different variables of the cost would affect the overall price. Does that kind of make sense? Okay, that's that slide. Now here you're just seeing like, I didn't want to do examples because I didn't think we had enough time. So look, if it's x squared, the derivative is 2x, and the differential is 2x dx. You will see in multiple calculus books, and I bet they talk about this in the How to Ace book, but it's not as simple as multiplying both sides by dx. I don't understand why it's not. Okay? Sorry, Con, I'm not going to be able to answer that question yet.
No, I think you might be able to.
Okay, do you mind if I pause?
Yeah.
And then if you're right, we're going to restate it, just so we can keep the video fun. Okay, Colin asked a great question, and it's like, okay, so are they literally just going to ask us to find the differential? And it's like, okay, they might when we get started. But without application, I think this is pretty useless. It's literally just one step from that. But yes, if they tell you the equation is y equals x squared, the differential is dy equals 2x dx, where the derivative is 2x. Okay? That's a good question. That's why I put this up. So look at some others. If the function is 2 sine of x, the derivative is 2 cosine of x, so the differential dy is 2 cosine of x dx. You get it. This is why we're not doing the examples. All right, so now you'll see what this is worth. This is a true engineering question. The volume of a ball bearing, estimate the propagated error of a ball bearing if we want our ball bearing to be 0.7 inches, but the measurement is correct within 1,000th of an inch. This is how engineers do things, okay? So we're trying to find the propagated error of volume. So what do you think we should start with? The volume of a sphere, okay? Hey, remind me, I want to copy that geometry page if you guys don't already have that. But does anybody know the volume of a sphere?
4/3 pi r cubed.
Very good. Okay. So now, notice, not an x. We're taking the derivative with respect to r. And that's going to be 3 times 4/3. So 4 pi r squared. So then dv is, the differential of v is
4 pi r squared times
dr, okay? Now what this is going to give us is a super close estimate. It might be exact, but it's not always, and we're going to have to read through the book to kind of see the difference. And that's the difference between absolute error and propagated error, I think. Okay? But it's okay. So now, our dV is 4 times pi times 0.7 times plus or minus, we'll just handle that in 2 steps. 0.00, right?
And then do you square the radius though?
Yes, sorry. Yes, squared. Thank you. I'll fix that right now before we do the math. Squared. Okay. Colin, will you do it times negative 0.01? And Alex, will you do it times positive 0.01? Oh, it's the same thing. I'm such an idiot. It's plus or minus. We didn't add them. I was looking for a range of acceptable volumes, but we're just going to get a plus or minus. So either one, what'd you get?
I got 0.061.
Can you confirm, Colin?
I'm gonna try to play the big calculator.
I have it over here on my laptop.
I had 6.15. I was
6 point.
I was 100 up, 100 times.
I feel like you're too big.
You said add and subtract.
No,
Right?
times,
Okay,
plus or
that's fine.
minus.
That's
My
fine.
bad.
Okay, that's why I was asking.
My bad.
That's it then, because.
All right, so that means that if we didn't have a caliber that would measure the diameter of our sphere,
We could.
then we could weigh it or take the volume of it. So we'd have to multiply by the mass, but you know what I'm saying. And then we would know if a sphere was within this given spec. Does that make sense?
So if we needed it to be correct within that spec, then
Yeah.
if we weighed it,
That's
then
right.
we would know. Okay.
That's right. I think this might be it, but let's see if I put another slide on here. Yep, this is the end of the last video. So by the way, this is the last video in Unit 3. We're all caught up.